Hello everyone, welcome to this video on learning mathematics through concepts and examples. In this video, we are going to solve some examples problem on application of derivatives and integration. So let's get started with our first example. Okay, example 1. Find two numbers with the difference 136 and whose product is minimum. So we need two numbers. So what we are going to do is we are going to assume two numbers first whose difference is 136. So we say, let the numbers be, okay, let the numbers be x and x plus 136, so that the difference between these two will be 136. Now what we need to do is we need to find the values of x and x plus 136 so that their product is minimum. So we need to find the product now. Now let's say that the product of these two numbers is denoted by px, which is equal to x times x plus 136, or when you simplify this, this will be equal to px equal to x squared plus 136x. Now what we need to do is we need to make this product minimum. In order to make the product minimum, we are going to use the calculus. So here I'm going to use the second derivative test to minimize this function. So let's find the first and second derivative. So the first derivative, p prime x, is equal to 2x plus 136, because the derivative of x squared is 2x and derivative of 136x is 136. And the second derivative, p double prime x, is equal to, we have to differentiate this, derivative of 136 is 0, derivative of 2x is 2. So the second derivative is that. Okay, once we get this, we need to know when is this product minimum. The product will be minimum at the critical point. That is when the first derivative is 0. So let's see, when first derivative is 0, what happens? When the first derivative is equal to 0, then we get first derivative is 2x plus 136 is equal to 0. And by solving this, we get x equal to negative 68. So we know that x equal to negative 68 is the critical point. So for x equal to negative 68, the product can be either minimum or maximum. We want the product to be minimum. And remember, for the product to be minimum, the second derivative must be greater than 0. Now, if you look at the second derivative, we have the second derivative equal to 2, which is greater than 0. Second derivative greater than 0, meaning of that is the product is minimum. This implies product is minimum. Okay, product is minimum at x equal to, it is minimum at the critical point at x equal to negative 68. So that means the numbers are, the first number is x, which is negative 68, and the second number is negative 68 plus 136. So now let's find the value of x plus 136. X is negative 68 plus 136, which is equal to 68. So x is negative 68, x plus 136 is positive 68. So these two numbers are negative 68 and positive 68. So the numbers are, okay, so the numbers are negative 68 and positive 68. So this is the application problem of the derivative. And here we use the second derivative test to find the minimum value of this product function, which is here. Okay, that is example 1. Now let's look at second example. A farmer wants to fence a rectangular area of 200 square feet next to the river. find the length and width of the rectangle, which uses the least amount of fencing if no fencing is needed along the river. Assume the length of the fence runs parallel to the river. So the meaning of that is, suppose there is a river. Let me show this in a picture here. Suppose here is the river, water flows here like that. Okay, that is the river. And fencing is done by the side of the river here. Okay, by the side of the river here. And to enclose this area, which is 200. 200 square feet is the area. Okay. Now, they say that assume the length of the fence run parallel to the river. So this is the length. So this is the width. Suppose if the width of this, okay, fence is X. If this side is X, if the fence has a width of X, then the length is equal to area divided by width. So that will be 200 divided by X. So this side will be 200 over X. And then the other side, this one is opposite of that X. So that will also be X. So once we know this, we know the total length of the fence. So here, the total length of the fence, I can write in terms of X, is equal to, this side we have X, this side we have X, 2X plus this quantity. So it is 2X plus 200 over X. And remember that here the value of X is positive. X cannot be negative or X cannot be 0 because it is the length. So X is positive. Now we want to find the least amount of fencing, okay, least amount of fencing material. Meaning of that is we want to find the minimum value of this function. So again, we are going to use the second derivative test here. So I'm going to find the first and second derivative. Now, the first derivative is equal to derivative of 2x is 2. And then derivative of 200 over x is negative 200 over x squared. And the second derivative would be derivative of 2 is 0. And then derivative of negative 200 over x squared is 400 over x cubed. So we got the first and the second derivative. Now what we know is the maximum or minimum value occurs at the critical point. That is when the first derivative is 0. So if the first derivative is 0, let's see what we get. If the first derivative is equal to 0, meaning of that is first derivative is 2 minus 200 over x squared is equal to 0. Or by solving this equation, okay, 2 minus 200 over x squared, if you solve this equation, you'll get x equal to 10. Remember, you'll get positive or negative 10, but the value of x is always greater than 0. So we only take the positive 10, x equal to 10. So that is the critical point. So at the critical point, we have either maximum or minimum. But to confirm that, we plug in the value into the second derivative. Okay, so here, if we want to find the second derivative at 10, this is equal to 400. Second derivative is here, 400 over x cubed. 400 over 10 cubed, that is greater than 0. Okay, so second derivative is greater than 0. Meaning of that is this implies the given function Lx, this one, or this equation, is minimum at x equal to 10. So meaning of that is if this is 10, then the total length of the fence will be minimum. That's what we know. We know that the length, okay, total length of the fencing is minimum at x equal to 10. And the question here is find the length and width of the rectangle. So we know that this side is the length. So we say that the length, because the question says, assume the length of the fence runs parallel to the river. River is here, so this is the length. So length is equal to 200 over x, or 200 over 10, which is equal to 20 feet. Okay, that is the length. We are asked to find the length and the width. Width is equal to, you can see here, the width of the river is x, okay, which is equal to 10 feet. So the length of the fence is 20 feet and width of the fence is 10 feet. So here also we use the second derivative test to find the minimum length of the fence. So we can use the second derivative test to either maximize or minimize the value of the function. Both of these are the word problems, and we use second derivative test to solve them. Okay. Time for example 3. Confirm that the below limit, this one, okay, meets the condition to apply L'Hopital's rule and then solve the limit. So we have to first confirm that we can apply the L'Hopital's rule for this one and then use that to find the limit. So here what we have is, we have limit as x approaches to 0 from the right of 3 sine x over 7 times the natural log of 1 plus x. So when x approaches to 0, the numerator will be 3 times sine 0, that is 0. And the denominator will be, if x goes to 0, this becomes natural log of 1, which is 0 times 7, that is also 0. So we get 0 over 0 form. 0 divided by 0 form. Now what we know is, if the function is in the form 0 over 0 or infinity over infinity, we can apply L'Hopital's rule. So this confirms that because we are getting 0 over 0, we can apply L'Hopital's rule. And L'Hopital's rule says, to find the limit like this one, we have to find the derivative of the numerator and the derivative of denominator separately until this 0 over 0 form is removed. So this is equal to limit as x approaches to 0 from the right. Now the derivative of 3 sine x is 3 cosine x. 3 cosine x. 7 is a constant. And then the derivative of natural log of 1 plus x is 1 over 1 plus x. So that means this is over 1 plus x. 7 over 1 plus x. Now we can simplify this a little bit and rewrite it like this. Limit as x approaches to 0 from the right. 3 cosine x multiplied to 7 over 1 plus x. This will go to the numerator and multiply. 1 plus x over 7. So once we get that, we'll try to do the direct substitution to see whether it works or not. So now, if we try to perform the direct substitution here, look carefully. When x goes to 0, 0 plus 1 is 1. And then cosine 0 is 1 times 3. So what I'm getting is 3 multiplied to 1 multiplied to 1 divided by 7. Because as 3 is a constant as it is, when x goes to 0, it becomes cosine 0. This one becomes cosine 0, which is 1. And this one becomes 1 plus 0, that's also 1. And over 7. So that means the substitution makes sense here. We can safely substitute like that. And we get 3 times 1, which is 3 over 7. So the limit of the given function using the L'Hopital's rule is equal to 3 over 7. Always remember, in order to apply the L'Hopital's rule, your function must be in the form 0 over 0 or infinity over infinity. If it is in some other indeterminate form, you have to change it to either 0 over 0 or infinity over infinity. Then you can apply the L'Hopital's rule. Okay, that is example 3. Let's move on to example 4, where you'll again use L'Hopital's rule. Okay. Example 4, find the limit using L'Hopital's rule. And here is our function. So our function is, let me write, here we have limit as x approaches to 0 of tangent 8x over x. When x approaches to 0, this becomes tangent 8 times 0. that is tangent 0 or 0. And the denominator is also when x approaches to 0, that is 0. So we have 0 over 0 form. So when we have 0 over 0 form, we can use the L'Hopital's rule. That means we find the derivative of the numerator and denominator separately. Limit as x approaches to 0. The derivative of tangent 8x is secant squared 8x multiplied to 8 divided by derivative of x with respect to x is 1. So basically, we are just getting limit as x approaches to 0 of 8 secant squared 8x. Now, if you use the constant rule, that constant will remain as it is. And then the derivative of secant squared 8x, we plug in x approaches to 0 means we plug in 0. So that becomes 8 times 0 is 0. Secant squared 0. Secant 0 is 0. So secant squared 0. And you know that secant 0 is 1. So 1 squared is 1. So 8 times 1. So that limit will be 8. So here also we use the L'Hopital's rule to find the limit. And this one was in the form 0 over 0. So one more time, in order to apply the L'Hopital's rule, your function must be in the form 0 over 0 or infinity over infinity. If it is in some other indeterminate form, we have to change this to 0 over 0 or infinity over infinity and apply the L'Hopital's rule. Okay, so we have done 2 examples on L'Hopital's rule. Now, example 5 will also be on L'Hopital's rule, but we need to do some manipulation first and then apply the L'Hopital's rule. Let's go for that. Example 5 here. Okay, find the limit. Use L'Hopital's rule if appropriate. So if you look at this function, let's see what we have. Here we have limit as x approaches to 0 from the right of square root of 7x multiplied to natural log x. When x approaches to 0, this function, the first function becomes 0 multiplied to, when x approaches to 0 from the right, log x goes to negative infinity. So this is 0 times negative infinity. And you know that 0 multiplied to a finite number is 0, but 0 multiplied to infinity, we don't know what is that. This is indeterminate form. So what we need to do is we need to change this to either 0 over 0 or infinity over infinity, whichever works. So let's see how we can handle that. Limit as x approaches to 0 from the right, we have natural log x multiplied to square root of 7x. This can be written as 1 over, in the denominator, square root of 7x, like that. Because when you write 1 over the reciprocal, it is same as this one. And now if we look at this carefully, the numerator is infinity, denominator will be 1 over 0, that will also be infinity. So basically this is in the form infinity over infinity. Infinity over infinity form. We have negative infinity in the numerator, but still the L'Hopital rules work here. Okay, when x approaches to 0 from the right, numerator becomes negative infinity, but the denominator becomes 1 over 0, that is infinity. Okay, so still infinity over infinity form is there, so the L'Hopital's rule can be used. Meaning of that is we have to find the derivative of numerator and denominator separately. This is equal to limit as x approaches to 0. The numerator will be, okay, so if we find the derivative of the numerator, derivative of natural log x is 1 over x. So we can write like this, 1 over x. We can write like that. And the derivative of 1 over the square root of 7x will be negative 7 over, we have to divide here. Dividing here is same as multiplying in the numerator. That is equal to negative 7 over 2 times, okay, over 2 times 7x raised to 3 over 2. You can find the derivative of this one and check it. Okay, derivative with respect to x of 1 over the square root of 7x will be equal to negative 7 over 2 times 7x raised to 3/2. That's why we write negative 7 and we are dividing by this quantity, which is same as multiplying by the reciprocal. So that's why we multiply in the numerator. Okay, once we do that, we can try to check whether we can simplify this a little bit or not. So first thing is, let me write here at the side. Okay, this is equal to limit as x approaches to 0. And then you can see here is 2. And here we are dividing by negative 7. That is a negative. So numerator will be positive, denominator will be negative. That means my answer will be negative. And then I'm going to keep this 2 first. Okay, I'm going to keep that 2 first, negative 2. And then in the numerator, we have 7x raised to 3/2. And in the denominator, we have 7 times x, 7x. 7x raised to 3/2 in the numerator, and then 7/2 in the denominator. This one, negative and 2 times 1 is written here. Let's simplify. We're just trying to simplify this. Limit as x approaches to 0 from the right, negative 2. And we have 7x raised to 3/2 over 7/2. I mean, 7x means we have the same base. We can reduce the power by 1. So 3/2 minus 1 is half, or it is just the square root of 7x. So that means once we use the L'Hopital's rule after this step, that's find the derivative in the numerator and denominator, and simplify, that's what we have done here and here, we get negative 2 times the square root of 7x. Now, if you look at this carefully, now this indeterminate form is gone. We can make direct substitution to find the value of the limit. Negative 2 multiplied to the square root of 7 times 0, because as x approaches to 0, that becomes 0, and the square root of 0 is 0, which is equal to negative 2 times 0 is 0. So the limit of the given function using the L'Hopital's rule, we get 0. Remember, we are not able to use the L'Hopital's rule directly. What we did is we first do a little bit of manipulation to change the 0 times infinity to infinity over infinity, and we use the L'Hopital's rule. Remember, whenever we have the indeterminate form, we can change that indeterminate form to 0 over 0 indeterminate form, or infinity over infinity indeterminate form, and then find the limit using the L'Hopital's rule. Remember, while using the L'Hopital's rule, we find the derivative in the numerator and denominator separately until we remove completely those indeterminates. Okay, time for example 6. So in this one, we are asked to find the antiderivative of this function. So let's see how we can find the antiderivative. So antiderivative, we write like this: antiderivative of 7x cubed plus 6x raised to 5 over x raised to 6. We are integrating with respect to x. Okay, in the variable x means we are integrating with respect to x. This is equal to, because we have a fraction here and we don't have the quotient rule for integration, we want to separate the denominator. So we have 7x cubed divided by x to the 6, 7x cubed divided by x to the 6 plus the second quantity is 6x to the 5. It also has the denominator x to the 6, integrating with respect to x. Now we can simplify. X cubed divided by x to the 6 is x raised to negative 3, and then plus 6 times x raised to 5 over x raised to 6. I can write that as 1 over x. And then to find the antiderivative of the first one, we use the reverse power rule. 7 is a constant, we keep as it is. In the reverse power rule, we increase the power by 1. So x raised to, if we increase the power by 1, negative 3 plus 1 is a negative 2. And we divide by that new power. Okay, and then plus integration of 1 over x is the natural log of absolute value of x, because the derivative of natural log x is 1 over x. We do the reverse. And then at the end, because this is the indefinite integral, we add plus c. So let's simplify to get the final answer. We have 7 divided by -2, which is negative 7 over 2. And then we have x to the -2. We have plus 6 times the natural log of absolute value of x plus c. So that is the antiderivative of the given function. So we use the power rule, and also we use the reverse of the derivative of natural log x. Derivative of natural log x is 1 over x. So integration of 1 over x is natural log x, because the antiderivative and derivative are the reverse process. So here I just did the reverse technique in the second term. Okay. Example 7. Here we want to find the antiderivative f of x of this function here. And the value of f1 is 0. That's given. So what they have given is here f of x is the antiderivative of this function, which is here, which is 6 plus 20x cubed plus 15x to the 4. Okay, so that is what we want to find. What is the value of that f of x? This is equal to antiderivative of 6 with respect to x is 6x, because the derivative of 6x is 6. Then plus 20 is a constant, so I can keep as it is. Antiderivative of x cubed, if you use the reverse power rule, that is x to the 4, we increase the power by 1 and then divide by that same new power, x to the 4 over 4. And then plus 15 is a constant. Again, we increase the power by 1, so x to the 5 over 5, then plus c. So that is our f of x. If we simplify, we get f of x equal to 6x plus 20 divided by 4 is a 5x to the 4, plus 15 divided by 5 is a 3, so 3x to the 5 plus c. So we get the antiderivative f of x, but that's not my final answer, because what they have given is f of 1 is equal to 0. So if I plug in 1 here, the value will be 0. That will help us to determine the value of c. Now let's use that. Now, if I want to find f of 1, so I plug in 1, 6 times 1 plus 5 times 1 raised to 4 plus 3 times 1 raised to 5 plus c. But it's given that f of 1 is a 0. 0 is equal to 6 plus 5 plus 3 plus c. 0 is equal to 6 plus 5 is 11. 11 plus 3 is a 14. 14 plus c is equal to 0, meaning of that is c is equal to -14. So to get the final answer, we need to plug in the value of c up here. So we can write our final answer. Let me write here at the side. So we say, hence f of x is equal to, I'm just writing this one now, which is 6x plus 5x to the 4 plus 3x to the 5. And the value of c we got here, it's -14. So we plug in -14. So that becomes -14. So that is the final answer. So we got the antiderivative, but we also used the condition given there to determine the value of c. So here we use the technique of substitution to determine the value of c, and we plug in back to the function here to get our final answer. So this is how we can compute the antiderivative. Okay, that is the seventh example for this video. Let's move on to the 8th example, example 8. Here also we need to find the antiderivative or the integral. So here, let's see what we have. I'm going to use the reverse technique of derivative to find the antiderivative. So here we have antiderivative of 9 over x minus 5 over 4 times the square root of x. dx. What I'm going to do is, I'm going to rewrite this function. So first one is 9 over x. I'm going to write that as 9 times 1 over x, because I know the function whose derivative is 1 over x. That's why I'm writing like that. And then minus this one, 5 over 4. I'm going to write that as 5 over 2. Okay, 5 over 2, and then 1 over 2 times root x. I have not changed it. It's 5 in the numerator, so 5 times 1 is 5. And then we have 4 times the square root of x. 2 times 2, that's 4x. But why I wrote it like that? Because I know a function whose derivative is 1 over 2 root x. So I know the antiderivative also. So what I mean by that, let's see. We have 9. The derivative of natural log x is 1 over x. So the antiderivative of 1 over x is the natural log of absolute value of x. The reason I'm writing absolute value is because I don't know the domain, okay? For the natural log, the argument of the function must be greater than 0. So to make the positive, I wrote absolute value. And then minus 5 over 2. I know the derivative of the square root of x is 1 over 2 root x. Derivative of square root of x is 1 over 2 root x. That means the integration of 1 over 2 root x is square root of x. And this is indefinite integral. So at the end, I need plus c. So that is the answer. 9 times the natural log of absolute value of x minus 5/2 square root of x plus c is the antiderivative of the given function. In other words, if you want to find the derivative of this function, you'll get this one. That's why the antiderivative of that is this, because the derivative and antiderivative are the reverse operations. Example 9 is still working on integration. So in example 9, we have, okay. So here we want to integrate 11 times t to the negative, e to the negative t over 3 dt. So the way we integrate this is like this. 11 is a constant. We write as it is. And you know that the integration of e raised to any quantity is the same. So that is e raised to negative t over 3. But the power of e is a linear function, negative t over 3. So we are integrating. So we have to use the reverse chain rule. That means we have to divide by the derivative of negative t over 3. And the derivative of negative t over 3 with respect to t is negative 1/3. Then plus c. So now if we simplify this, 11 divided by negative 1/3 is negative 33. Negative 33 e raised to negative t over 3 plus c. So that is the antiderivative of the given function. And we use the reverse chain rule to determine the antiderivative of e to the negative t over 3. Time for example 10. Okay. Let's see what we have in example 10. Here we want to find the indefinite integral or antiderivative of x raised to 1 over 12 minus 5 sine x dx. Okay, for the first part, x raised to 1 over 12, we use the power rule, the reverse power rule, because we are integrating. So what we do is we increase the power by 1 over 12 plus 1, and we divide by that new power, 1 over 12 plus 1. Then minus 5. 5 is a constant. We write as it is. And then the antiderivative of sine x is negative cosine x, because the derivative of negative cosine x is sine x. Antiderivative is the reverse process. So the antiderivative of sine x will be negative cosine x. And at the end, we add the constant of integration. Now, you can see here we have 1 over here in front. There is nothing, means the coefficient is 1. 1 over 12 plus 1. 1 over 12 plus 1 is 13 over 12, and it is 1 over. That means we take the reciprocal, which is 12 over 13. 12 over 13 times x raised to 1 over 12 plus 1 is 13 over 12. 13 over 12, and then this one negative, and this is negative. Negative times negative is positive 5 cosine x plus c. So that is the antiderivative of the given function. That was example 10. Okay, we have few more to go. Here comes the 11th example. Okay, in example 11, this is the problem on Riemann sum. Okay, we have to estimate the area under the graph of this function from x equal to 0 to x equal to 5 using the Riemann sum with n equal to 10 subintervals and right endpoints. So the first one has right endpoints or right Riemann sum, and the second part is using the left end points or left Riemann sum. So everything else is the same, but we have to use the left and right Riemann sum. So there are a few standard steps that you need to remember in computing the or estimating the area under the curve using the Riemann sum. So first thing is you have to find the delta x. So I'm going to do A here. Delta x is b minus a over n. Okay, delta x is b minus a over n. So x equal to 0 to x equal to 5. So this is your a and this is b. So b minus a will be 5 minus 0, which is 5, divided by n. N is the number of intervals, subintervals 10. And 5 over 10 is a half, or 0.5. That is first step. The next step is you have to find xk. Xk is different for different Riemann sum. For the right Riemann sum, the value of xk is a plus k times delta x. A is 0 plus k times delta x is half. Delta x is here, that's a half. So 0 plus k times half, that is simply k over 2. K over 2. That is the second step. Then third step is you find f of xk. You plug in this value into the given function. So if I plug in here into that function, it will be 1 over, in place of x, it is k over 2 plus 1. So these are the three standard steps that you have to follow first. Delta xk, and f of xk. Now, the Riemann sum says the approximate area is equal to summation k equal to 1 through n, whatever the number of interval may be. Okay, f of xk times delta x. So that is equal to summation, in this case, k equal to 1 through n means we have a 10. F of xk we got here, that is 1 over k over 2 plus 1. And we have to multiply that by delta x. Delta x is half. Delta x is half. And you can simplify this using any computer or calculator. So if we type all this in calculator, you should get 0.5244. So that is our right Riemann sum. Okay, that is our right Riemann sum, 0.5422. Remember, this is the approximate value. So if we draw the graph of this function and we want to find the area under this graph from x equal to 0 up to x equal to 5 bounded by x-axis, the approximate area will be 0.5244. Okay, that is the right Riemann sum. Now let's work on left Riemann sum. Remember, the process is pretty much the same. The only difference is when you find xk. So delta x first, which is b minus a over n. We have exact same question. So 5 minus 0, which is 5 over n is 10. So 5 over 10 or 1 over 2. That is the first part. Now we find xk. xk for the left Riemann sum, okay, left endpoint will be a plus k minus 1 times delta x. Okay, it is a plus k minus 1 times delta x. Now the value of a is 0, so that is equal to 0 plus k minus 1 times delta x is half, which is equal to k minus 1 over 2. So the value of xk is k minus 1 over 2. So third thing, f of xk. F of xk means we plug in this into the function. So it will be 1 over k minus 1 over 2 plus 7. Plus 7. If you look at the previous function, it was plus 7 here also. That was a little bit of error there. So plus 7. But remember, once I type this in the calculator, I get that value. That part is correct. Okay. So we get f of xk. Now let's find the area. Now, area is approximately equal to summation k equal to 1 through n f of xk times delta x. Remember, some textbook use xi, that is the same thing, which is equal to, now this is equal to summation k equal to 1 through n is 10. And then f of xk is this one, which we get here, 1 over k minus 1 over 2 plus 7 multiplied with delta x, which is half. One more time, if we use TI-84 calculator or any other calculator that handles this summation and type it, okay, we get the value, which is 0.5542. Remember, whether you use the left Riemann sum, right Riemann sum, or midpoint Riemann sum, the values should be pretty close. Okay, so this is our left Riemann sum here. That is the right Riemann sum. They are pretty close. If we use the midpoint Riemann sum, the value will be more accurate. In case of left and right Riemann sum, if you keep increasing the value of n, also true for the midpoint Riemann sum. If the value of n is really, really large, then the area will be more and more accurate. But these are the approximate area. That's why I use that notation here. Area is approximately equal to. Area is approximately equal to. And also in the question, they use estimate because it's not going to be accurate, but it will be approximately equal. That's why we have the word estimate there. So we estimated the area under the curve from x equal to 0 to x equal to 5 with the 10 subintervals using the right and the left Riemann sum here. Left endpoints means you are using the left Riemann sum. Okay, left endpoint means you are using the left Riemann sum. Right endpoints means you are using the right Riemann sum. Okay. So now finally we are here in this 12th question. This is the last question for the day. And here we are again estimating, as you can see, okay, we are again estimating the area under this graph, f of x equal to square root of x plus 4, from x equal to -1 to x equal to 2, using, okay, Riemann sum, n equal to 10 subinterval, but this time we are using the midpoint Riemann sum. Okay, we are using the midpoint Riemann sum. Process is exactly the same, except the step where we find delta x. So let's begin. I mean, where we find xk is a little different. Delta x is same. Delta x is b minus a over n. Okay, delta x is b minus a over n. So here in this one, b minus a means 2 minus a -1. That's a 3. Okay, 3 divided by 10. So delta x is 3 over 10. Next, we need to find xk. Xk is equal to a plus k minus half. This is the midpoint, so k minus half delta x. So we need to plug in the value and simplify. A is -1, -1 plus k minus half times delta x. Delta x is 3/10. 3/10. So it will be -1. Now if I distribute that, that's plus 3k over 10 And then if I distribute here, that is minus 3 times 1 is 3. And then 10 times 2 is 20. So now if we simplify this little further, 3k over 10, and then negative 1 minus 3 over 20 is negative 23 over 20. Negative 23 over 20. So that is xk. We find delta x. Now you can see that for the midpoint Riemann sum, xk is a plus k minus half times delta x. We plug in the value of a, we plug in the value of delta x, and we simplify to get this one. Next thing is we need to find f of xk. F of xk means we plug in this value xk into the function. Our function is square root of x plus 4. That means it will be square root of this quantity plus 4. Square root of 3k over 10 minus 23 over 20 plus 4. And we simplify that. This is equal to square root of 3k over 10. And then 4 minus 23 over 20 is 57 over 20. 57 over 20. So we get that value, f of xk. Now we can easily estimate the area under the curve. Now what we know is from Riemann sum, area is approximately equal to summation k equal to 1 through n, f of xk times delta x, which is equal to summation k equal to 1 through, in this case, the number of interval is 10. And then f of xk, we got it here, which is square root of 3k over 10 plus 57 over 20 is that function. And we multiply that by delta x, which is 3 over 10, which is 3 over 10. Now, if we simplify that using calculator, we should get 6.3342. So that's how we can use the midpoint Riemann sum to estimate the area under the given curve. And that is the last example for this video. Thank you so much for watching, and I hope you find this video helpful.